Confidence interval for the mean using the z-table. Example, a sample of n equal 15 patients. The mean creatine level x bar is 1.4 milligrams per deciliter. This is taken from a larger population. In the population of all potential patients, the creatine level is normally distributed with mean mu, which is unknown, and known standard deviation sigma 0.5 milligrams per deciliter. Usually, if the population mean is not known, the standard population standard deviation will also not be known. But this is it doesn't quite match what would usually happen in practice. Although the advantage of this method is that it follows directly from the central limit theorem, I guess is one thing, and also even if sigma is not known, if you have a very large sample, the probabilities will be very close to what we're doing here with the z-table. Okay, so anyway, part A, we want to find a 95% confidence interval for the unknown population mean. Our desired confidence is going to be 1 minus alpha. That's 0.95 or 95%. And alpha itself will be our level of doubt. 1 minus 0.95 is 0.05 or 5% doubt. And we want to push, this is for a two-sided confidence interval, we want to put half for a doubt at each extreme. So we'll have alpha over 2 is 0.025 on each extreme here. And then, so using the z-table in reverse, we want to look up 1 minus alpha over 2. 1 minus alpha is 0.95, but because our z-table, the way our table is set up, it only shows the probabilities of z being between 0 and the number. It doesn't show this piece here. So instead of looking up 0.95, I'll take half of that, look up 0.475, and I'm using the table in reverse, and it's in the 0.4750 is in row 1.9, column 6. So the z-score that goes with that probability is 1.96. Okay, in the next step, we can plug into this formula here. We'll have a lower bound and upper bound for our confidence level, and it's the same formula except for the sign in the middle. So for the lower bound, it's x bar minus the z-score times sigma divided by square root of n. So putting in the numbers, our sample mean 1.4 minus 1.96, that's the number from the z-table, times 0.5, that's sigma divided by square root of 15, that's the square root of n. And I'm computing what comes after the minus sign separately, because sometimes that's reported separately. 1.96 times 0.5 divided by square root of 15 comes out to be about 0.253. That's called the margin of error. And if we subtract, we get approximately 1.15 milligrams per deciliter. Then the upper bound is going to be the same, except we're going to be adding the margin of error, and that comes out to be 1.65 milligrams per deciliter. So that means we are 95% confident that the mean creatine level in the entire population of patients is between 1.15 and 1.65 milligrams per deciliter. Part B reports the margin of error. As we mentioned above, it's approximately 0.25 milligrams per deciliter. Okay, so according to the central limit theorem, these confidence interval formulas for the mean are valid if the population standard deviation is known and either n is at least 30 or the variable is normal. Here's another example. Standard deviation of lung capacity is 0.4 liters. Researchers wish to determine mean lung capacity in liters with 97% confidence and a margin of error of less than 0.1 liters. How large should the sample size be? So now, before you take a sample, it's sometimes helpful to know how big the sample should be. If the sample is too small, it may not give you the results that you want, and if the sample is too big, you may be you'll have the results that you want, but you may be spending more money than you need to spend. Maybe you get the same results or with a smaller sample. So it's helpful to sort of think in advance of taking a sample how big the sample size should be. So we decide here, in this example, we decide ahead of time that we want 97% confidence and a margin of error of less than 0.1 liters. Okay, so our confidence level 97%. That's 1 minus alpha, and then we have half the doubt on each side. There's 3% doubt, and half of that is 0.015. That's half of that on each side. So using the z-table in reverse, we're looking up the 0.97 divided by 2 is 0.485, and look for that using the table in reverse. It's row 2.1, column 7. So our z-score is 2.17, and then if we plug it into this formula here, n has to be at least 2.17 times 0.4, which is sigma, divided by our desired margin of error is 0.1, square this, and it comes out to be 75.34. Now it's not possible to sample a fraction of a person, so if you want our error to be less than 0.1 liters, you have to go, you can't round down. You have to go, even rounding down is closer, you have to round up in order to make sure the margin of error is less than 0.1 liters. So round up to 76 people. And that concludes this presentation.